In this video, we're going to be looking at the fairly unique equilibrium system formed when water reacts with itself. When we looked at amphiprotic compounds, we saw how water can use one of its lone pairs to form a bond with a hydrogen on another water and take it away, thereby forming hydronium. Therefore, we know that water can act as an acid. Conversely, when the second water molecule loses its H+, it will form hydroxide, thus showing that water can behave as a base as well. We can look at either the transfer of H+, or the fact that the reaction produces both hydronium and hydroxide to show that water is acting as both an acid and a base in the same reaction. Now, the more interesting aspect of this is that this reaction is fully reversible, meaning that hydroxide can use one of its lone pairs to reform a bond with the extra H+ on hydronium, breaking the bond and returning it to being a lone pair on oxygen, thus creating two water molecules and getting us back to our starting reactants. Because of this, we can write an equilibrium expression as well as a KEQ formula for the reaction with water with itself, where we have as our only reactants two water molecules that exist in equilibrium with both hydronium and hydroxide ions. This looks a little bit different than the KEQ expressions for acids and bases, Ka and Kb, because water is the only liquid within this equilibrium system, meaning that it is a pure liquid, and because its concentration remains constant because it's the solvent, we do not write it in the KEQ expression, and instead we only have the concentration of hydronium times the concentration of hydroxide for our equilibrium expression. Now, because water is functioning as both an acid and a base in this reaction, we cannot use Ka or Kb to represent its equilibrium expression, instead giving it the unique equilibrium constant value of Kw, meaning the KEQ of water reacting. And if we look at it on a Rice table, we can see some specific patterns occur that are unique to water as far as acids and bases go. Using the relationship of enthalpy and entropy to understand which direction of the reaction each favors, we can see that entropy clearly favors the formation of the products because we're going from, even though we have the same number of particles in our reactants and products, aqueous ions exist in a more disordered state than liquid water molecules do because the hydrogen bonding structure of water molecules with each other is relatively predictable, but they get less predictable when we introduce ions with full charge. Now, if entropy favors the production of products, that must mean that enthalpy must favor the reactants in order to give us the equilibrium, and therefore we can conclude that delta H is in the reactants. Therefore, if we increase temperature, it would shift the equilibrium towards the products, but since the mole ratio of hydronium to hydroxide is 1:1, that means that the ratio of change for hydronium and hydroxide is always going to be the same as long as our water is pure and we do not have any extra acid or any extra base within this reaction. The conclusion of this is that the concentration of hydronium and the concentration of hydroxide in pure water is always going to be equal, and this is why water is so unique in that water, pure water anyway, is the only known neutral substance because by nature of its equilibrium, it always produces an equal amount of hydronium and hydroxide. And if we know what the magnitude of water's equilibrium constant Kw is, we can actually calculate what the concentration of hydronium and hydroxide are in an equilibrium. At 25 degrees Celsius, which is the standard atmospheric temperature, our Kw value has the approximate value of 1.0 times 10 to the negative 14, and this is not accidental. So if we use this to calculate what the concentration of H3O plus and OH minus is, assuming that that value is X, assuming that we have pure water and our initial concentrations of each ion are 0, that means that our Kw 1.0 times 10 to the negative 14 is simply equal to the concentration of H3O plus times the concentration of OH minus, which we can see from our Rice table is going to be X times X, which is simply X squared. So to solve for X, all we need to do is take the square root of 1 times 10 to the negative 14, and the way that square roots work, all that we need to do is divide our exponent by 2, which means that we would end up with X being 1.0 times 10 to the negative 7 as being equal to our concentration of H3O plus and the concentration of OH minus. Now this number here is not accidental. If we remember that the pH of pure water is 7, and we know that pH is equal to the negative log of the concentration of H3O plus, if we take the negative log of 1.0 times 10 to the negative 7, we end up with 7. So this here, based on the equilibrium constant of water at 25 degrees, explains why pure water at room temperature has a pH of 7, and it is all based on this equilibrium system here. In the next video, we're going to look at how we can use Kw in order to extrapolate some conclusions about the Ka and Kb of other acids and bases.